Welcome, dear students. This time I welcome you again to this vector, this calculus. It is lecture number 21 on again volume integrals. I have already told you when I delivered a lecture, that was 20th lecture on volume integrals, where we introduced the volume integrals. 20th lecture on vector calculus, and there we introduced what we mean by volume integrals. I have already told you we will give you the significance, physical significance of this volume integral. You see, as I said in lecture number 20, that what is this volume, how we calculate it when we have any solid in 3D surface bounded by four walls. It may be your cuboid, it may be your cube, it may be even a sphere. When we integrate any function over its volume, any function when we integrate over its volume gives in simple language volume integral. Then we have also derived the formula for finding out this volume. Now today I want to actually give you the physical significance of this volume integral, what it actually represents. Okay. Well, you know, in your previous classes, in your previous semesters, you have already done and evaluated so many problems on this double integral, triple integral, double integral on functions of two variables, even triple integral over volume. I want to pose you a question here, if some of you can give answer. It is, what actually this volume integral represent? When you evaluate any three variable function over the volume, you find the triple integral of any three variable function over volume V. You get some result. Do you know what that result actually represents? Yes, some of you must be knowing. It actually represents the mass of the volume. It represents mass of that volume. Mass of what? You see, the triple variable function, when you integrate it, the three variable function, when you integrate it over any mass, any volume, when you integrate it over any volume, when you evaluate the triple this integral over that volume, that gives mass of the volume. Why? Because you know that the volume surface has the matter. It is composed of matter. Matter particles have the density. When we find out that when we multiply the density with its volume, what it gives? It gives mass. When we multiply any density of the matter in the volume, density of the matter particles in the volume, multiply that with its volume, then what you get, density into volume, gives you mass. It represents the mass of that volume. Triple integral over the of the any function over the surface over the volume V. Well, if you take any point on this volume, the value of the three variable function at any point of the volume actually represents the density function. It is known as sometimes as density function. When we multiply that density function with the volume, you get mass. This is the simple, in simple words, we say that volume integral of the function f of xyz over any volume V gives what? It gives the mass. On the basis of this, I am sharing this in this video. Another definition, you may say, another interpretation, another explanation that gives you the significance of the volume integral. Let us count. Let us understand. Let us count this. Well, this is your, as previously we did, this is your surface bounded by four faces. It may be cuboid, it may be cube, it may be any other surface. It has has the volume V. Consider any closed surface in space enclosing volume V, as we did in lecture number 20, just like that. By definition of the volume integral, we have derived the definition of volume integral. We did there, volume integral is given by this. if f is a vector point function or even scalar point function, volume of the f over v dv is given by this. Then we have seen how this dv is get it converted in dx dy. These are in rectangular coordinate system. Okay. Let f of xy be density of 3D solid. Now I have told you it is now every point on the volume represents what? It is the density of the matter, density of the volume. Let f of xyz be density of 3D solid at point xyz. Now to define triple integral, divide the given volume, that is this volume, in small boxes or small cubes. We divide it in small boxes or small cubes, say with dimensions delta x, delta y, delta z, small volumes for the cube or box at ijth place. Just look here, I have divided this volume into small cubes or boxes. I take this box or volume, this I take at the ijth place. What does that mean? At the ith row, jth column and kth layer, ijth place. At ijth place, this smaller volume, whose value this volume we denote by dv, it is del x, del y, del z, del x, del y, del z. It is del z here. I will just change it. It is delta x, delta y, delta z. It is delta v is delta x, delta y, delta z. We are using here mass is equal to density times volume formula, which gives you mass. Okay. We have the change in given volume, this, that is delta v is change in the volume at the ith row. This is the change in the volume in the jth column. It is the change in the volume in the kth layer. So this is, we take here the point P. This delta v is delta x, delta y, delta z, just like length, breadth and height that you give in case of volume. Well, I have written here for the cube box at the ijth place. This is the box or cube at ijth place. Okay, small volume of volume delta v. When we divide this into smaller volumes, then the idea is same. We tend finally tend to infinity. Then you get the triple integral what you saw. At the ijth place, the point, this point P. Here I take a point P. It is x ijk, y ijk, z ijk. The point at the ith row, jth column and kth layer. This point we take. When we find out the value of the function at this point, I have told you that every point on the volume of f of x, y, z, when we take any point on the this volume, the value of the function, three variable function at that point represents density of the matter contained in the volume. Okay. In other words, we can say density of the box or the density of the cube is given by f of x, y, z, y ijk, x ijk, y ijk, z ijk. What does this ijk stand for? We took a smaller volume, we choose a smaller volume at ith row, jth column and kth layer, and we denote the volume at that change in volume, that delta v, and corresponding volume in terms of length, breadth, height, the smaller volume is given by delta x, delta y, delta z. Okay. Now mass is given by density times volume. Mass is density times volume. We write here what is our density of the volume. It is the value of the function at any point, that is point P. It is f of xij, y ijk, z ijk. Delta v is the volume of this box or volume of this cube. Then by summing up these approximate masses, this is the volume at this. Similarly, you can find out the mass at this smaller masses, m1, m2. If you denote the masses at this, you denote the mass of this by m1. Say it is m1, mass of this at m2, mass here m3. You find out different masses by using the same. Choose any point here in the volume, find the value of the function at that point. That what that represent? That represents u when you find out the value of any point at this smaller volume, that will be the density. When you multiply the density by this volume, what you get? Mass m1. When you take here any point, you find the value of the this function at this point, which lies at this volume. That will give the density of this portion at point P, P2 say. Then when you multiply value of the function at that point P into the volume of this box, that gives M2. Then we write by summing of these approximate masses, we get total mass of the given solid. It is the, so what you say now, we conclude that the this volume integral physically means it gives the mass of that solid on which we integrate the function on the volume of the any solid. It gives the mass of that solid where we integrate any function on the volume of that solid. This is what we mean by this physical significance of volume integral. I hope you have understood. There are now two definitions. Now in case this also, when you, the definition is same, when we make the this number of subdivisions tend to infinity, let that number here, it is finite. When we make the number of subdivisions let tend to infinity, finally when n tends to infinity, each volume tends to 0. When each volume tends to 0, it is the concept of definite integral that gives you the definite integral. Then that definite integral will be called the volume of the given integral, volume of the given integral, given function, sorry, volume of the given function at V. That concept is same as we did in previous. In this small lecture, I have given you the what we mean by actually the significance of volume. It is nothing. It is the mass. It represents the mass of this whole solid on which we are integrating the given function on the volume. Then by summing up these all masses, we get the total mass of the solid. I hope you have understood this. Now let us have some applications of this. I will share with you the application of this. I will write the application here, then it is solution. Let me write the application now. Well, my dear students, I want to do here some application on this volume integral. This is the application on volume integral. You may take it as a first application. We may share one or two more. It is if f is the vector point function given by 2xzi minus xj plus y square k. Okay. Evaluate the volume integral of f dv where v is the region bounded by, it is the region bounded by surfaces x0, y is equal to 0, x is equal to 2, y is equal to 6, z is equal to x square, and z is equal to 4. This is actually given the region. Where you say the limit of integration, you may also say. Let us have it as solution, how we solve such problems, how we find out the volume integral of this. Okay, we have the solution part of this. I will write the solution of this problem. Solution is this. We have to evaluate volume integral of f over v dv, and you know what is this equal to by your previous lectures. Volume integral of the volume v is bounded by these surfaces. F dv is actually volume integral of v f over dx dy dz. You know how it is converted this. Well, you have f, you will use the value of f. This is equal to triple integral over v. It is the value of x is given by 2xzi minus xj plus y square k. It is dx dy dz. In my previous lecture, this was actually the 20th lecture, where I told you we may have functions of two types. One is the vector point function, second is the scalar point function. Now this is actually the vector point function, how we evaluate this, you know about this. This gives you three integrals. It is integral I, volume integral over V, you can 2xz, then minus j, volume integral over the volume V of x dx dy dz, it is this one, then plus k, volume integral over V of y square dx dy dz. Okay, you know that this given volume integral has got converted into three this integrals. So volume integral of given vector point function f over V is given by, I will denote this by I1. This integral I will evaluate I1, this is minus I2, and this is your plus I3. Let this be equation number 1. I will find out this volume integral, this triple integral. Now it is a triple integral. This is here dx dy dz. I am sorry, dx dy dz is must here. It is dx dy dz, dx dy dz. Yes. Do you follow? Okay. Let us find now I1. What is your I1? This is this integral I times triple integral over V to xz dx dy dz. You can write this as, this is 2i, it is constant, write it 2i out. Here we have the range for x running from 0 to 2. I will write here x is from 0 to 2. It is a constant range here. Here you have y running from 0 to 6 here. This 0 to 6. Then you have here integral z running from, it is x square to 4. X square to 4. Then it is your xz dx dy dz. Well, this range is here constant. For x it is constant, for y it is constant, for z it is the variable. I will first integrate this function with this z first, because you have this range, what, variable. First you take the variable part. Okay, let me rub this one. But I will remember here what I have this, my I1, what is my I1 here? It was I times triple integral V to xz. What it was I2? It was j times, in fact minus j times, not minus, I will minus there, triple integral V, it is j is x, it is x. It is dx dy dz, here it is dx dy dz. Then what is your I3? This is unit vector k times v over y square dx dy dz, and our volume integral is what, I1 minus I2 plus I3. I will note down them here so that I can rub here everything. Let me rub it. I don't need it now. Now my I1 is, I am finding I1, my I1 is here 2i times integral x range is 0 to 2, then y range is 0 to 6. I will first integrate with respect to z, integral of z going from x square to 4. It is z, x is constant here, out, x out, z dx, gz, sorry, dz. This is your dx dy. Do you follow? Because this is here range variable, we first integrate with respect to z. For the z range we have variable. This is your 2i integral 0 to 2 x range 0 to 6 for y. Let us integrate this, x is out. This will be your z square by 2 integral from z running from x square to 4 dx dy. I hope you are following me. Now I don't need this thing. I rub it. Just see what we are doing. Then this 2 and this 2 will go. It is I times 0 to 2 for x, 0 to 6 it is y range x. Give the upper limit here 4, it is 4 square minus x square whole square, it is x4. It will be your dx dy. Okay, this is your I times 0 to 2, 0 to 6, this is 16, 16x minus x5 dx dy. You have here x range, I can take it by the process of double integration. This way I can integrate it. For x range I have this, I can write it I, this time it is 0 to 2, 16x minus x5 dx. Then it is here constant 1, integral 0 to 6, 0 to 6 it is 1 dy. 0 to 6 here coefficient of dy is 1. We can use the product method by double integration. We can do it. Well, you have this I1 I am finding. Do you follow me? I1, this is integral I. What is the integration of this? 16x with respect to x. It will be 16x square by 2. That is only 8x square. 8x square. 8x square ranges from 0 to 2. This I is out. Then what about this x5? It is minus x6 by 6. Do you follow? Ranges from 0 to 2. ये separate हो जाएगा. Integral of this, it is y. Ranges from 0 to 6. Now let us evaluate this integral. So I am getting I1 here. Be cautious what I am doing. I1, it is I times unit vector. Give the upper limit here. 8, it is 8 into 2 square. Is it 2 square? X square by 2. Yes, it is 2 square. It is 4. Then minus 1 by 6. It is 2 raised to power 6. 2 raised to power 6 minus 0. Then outside it is 6 minus 0. When you give the upper limit 6, lower limit is 0. This is I1 is I times 32 minus, this is this will be 32 by 3. Why? Because 2 raised to power 6 is your 32 into 2. Then you take 2 raised to power 6, it is 64. I can write it 32 into 2. Why 2? Because you can cancel this 2 3s are. Okay, this is 6 only. This is I1 is equal to I times, take 32 common, it is 1, it is 2 by 3 only, it is 6. This is your 3, 2s are, this is I1 is I times 32 into 4, this is 128I. So therefore we have got I1. I don't need this one here. I will note down here my I1 is, I1 that I have found, it is 128I. I1. Okay. Now let us go to find out I2. We will now find out I2. Just look, what is my I2 now? My I2 is j times triple integral of x dx dy dz. Write down the range here. x के लिए है 0 to 2, y के लिए है 0 to 6, z के लिए है z is what is z के लिए क्या है x square. It is x square. Z is x square to 4. Then it is dx dy dz. Here also you have for the range z square variable range z. So I will integrate first this portion with this z. Okay, write it as j times integral 0 to 2, 0 to 6, it is for y. I will take it x square to 4. This is your, you don't have here, you have here x, you have here only x. Take this x out for the timing, it is constant. It is your 1 dz, then dx dy. This will be j times integral 0 to 2, x is here, 0 to 6. This is your z from x square to 4. You can take x here because this is converted to x. dx dy now. This is equal to j times integral 0 to 2, integral 0 to 6. It is your x times 4 minus x square dx dy. This is your j. I am finding out I2 this time. 0 to 2, integral 0 to 6. It is 4x minus x cube dx dy. Now we shall take dx with this and it is own limit. What that give you? It will give you this way. It is j integral 0 to 2 for x, then 4x minus x cube dx into second integral y into multiply rule 0 to 6, it is 1 dy. I hope you are following me. Well, now you will take I2, we are finding this is j times here integral of 4x with respect to x, it is 4 x square by 2, limit is 0 to 2 for x, then minus integral of x cube, it will be x4 by, yes, 3 plus 1, 4, again from 0 to 2, close this, then integral of this is y from 0 to 6. Let's just evaluate this. I2 is j times 2 goes here, it is 2, it is 2 square minus 0, this is minus 1 by 4, it is 2 raised to power 4 minus 0, and this is only 6 minus 0. Let me simplify this. I2 is j times 2 2s are 4 2s are 8 minus, this will be here 32, no 16, 2 2s are 4, 2s are 8, 2s are 6, 16 by 4, it is your 4, this is your 6. Well, it is I2 is j times, it is 4 into 6, this is I2 is 24j. This is I2. Therefore, I will write here my I2 is what? It is 24j. This is I2. Then we have to find out I3. Then what is our I3? Our I3 is now k times unit vector k triple integral over v. It is y square dx dy dz. Give the limits here as you did previously. This is I3 is k times integral x going from 0 to 2, y ke limit 0 to 6, and z is from x square to 4. This is y square dy dx dy dz. Here also for the variable limit, we will first integrate the variable, the integral which has the variable limit. It is this. We integrate this with dz. Sorry. This is your I3 is k times integral 0 to 2 integral 0 to 6 for this. Then y square I will keep out. It is integral of x square to 4 1 dz, then it is dx dy. This is your k 0 to 2 0 to 6. This is y square. It is value is z. Integral of 1 with respect to z is z. Give the upper limit. It is 4 minus x square dx dy. Because integral of 1 with respect to z, if you are confused, let me write this way also. It is z from x square to 4 dx dy. This is k unit vector 0 to 2 integral 0 to 6 y square. Give the upper limit 4 minus x square dx dy. Be cautious. This is here product. We will take this with x and this with y as we did previously. This is the product. This is known as product rule. Double integral. Well, your I3 is now it is k times integral 0 to 2, it is for x. This you can write 4 minus x square dx. The x function you take, it is product with this x limit, and this is y limit into y running from 0 to 6. It is y square dy. Now be cautious. It is here we are taking the multiple rule for double integrals. We have done these in double integrals. Well, this is now unit vector k. Integrate this 4x. It is 4x integral of 4 with respect to 4x. Limit is for x 0 to 2 minus integral for it. This is x cube by 3. Be cautious. It is 0 to 2. Then for this y 3 by 3 from 0 to 6. Let us evaluate this. It is k times 4 out. It is 2 minus 0. Then minus 1 by 3. It is 8 minus 0. This is 1 by 3. This is 6 raised to power 3 minus 0. Now what it gives me? This is k into 8 minus 8 by 3. This is 36 into 6 by 3. This way you can also go. This gives you I3. It is k times 8 into 2 by 3 into 36 into 2. Now you can multiply it. You just multiply it now. क्या आ रहा है ये? What is it is 384. This is I3 is 384 k. You can also correct it if I am doing well. Multiply 8 is 64 4 36 4 384. So what is the required volume integral? Required volume integral. Thus thus required volume integral is triple integral volume integral over V f dv, that was I1 minus I2 minus I2 plus I3. What is your I1? 1, 2, 8I. What is your I2? It is minus 24J. What is your I3? It is plus 384K. This is the required. I have already told you, sometimes it gives you the vector and sometimes it gives the scalar, and in this case this volume integral is what? It is a vector function. Well, dear students, this way you have come to know how we evaluate the volume integral. We may share one or two more examples here for evaluating the volume integral, how we evaluate it. I hope you have understood it. Thank you very much, and wait for the next lecture soon.